Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor in the Department of Computer Science at Jesus and Mary College, University of Delhi. So friends, welcome to this discussion on operating systems. As you would know that in the previous lecture of this series, we were talking about memory management and we were actually discussing how the binding of instructions happens when program execution is happening. So basically we were talking about the process, the different stages in the program execution when the binding can happen and what are the repercussions. So first foremost stage at which the step at which the binding of the instructions and data to memory addresses takes place is in the compile time. So if at the compile time it is known that where the process will reside in the memory, right, then the absolute code can be generated. The compiler can use the absolute code, right. So if you know that a user process will reside starting at location R, right, then the generated compiler code will start at that location and extend up from there, right. So if at some time later the starting location changes, say for example it becomes R plus 1, then it will be necessary to recompile this code because the location has now changed. The compiler was given another location, now the starting location has changed, so the recompilation has to be done. So this was this kind of binding with the location happening at the compile time was done in the MS-DOS operating system format. Now next is that the load time, if it is known instead of being known at the compile time, it is known at the loading time where the process will reside in the memory. Then the compiler must generate the relocatable code. Why relocatable code? Because the final binding is to be delayed until the load time, because at the compiling time it is not known where the process is going to reside. So what will happen at the loading time, the relocatable address is to be generated. So now if the starting address changes, then we need only to reload the user code to incorporate the change value. We don't have to compile the code again, we only have to reload the user's code, right. And then the third is at execution time, that is if the process can be moved during its execution from one memory segment to another, that is the location or the address will change during the compilation, then the binding has to be further delayed till the runtime. So it's not at the compile time, not at the loading time, but now the binding will happen at the runtime, right. And the runtime binding of memory address space is most commonly used in all the operating systems. So now we know that the different stages at which the binding can take place, and while we were discussing this, we had also talked about something called the virtual address or something called the relocatable or the symbolic address, etc. There are two very important terms which are used to denote the address space of within a computer or address of the memory. These are the logical address space and the physical address space, right. Now the address which is generated by the CPU is actually a logical address, right, whereas the address which is seen by the memory unit, that is the one which is loaded into the memory address register of the memory, is referred to as the physical address. So CPU is generating the logical addresses, but memory unit is looking at the addresses which are actually physical addresses. So what we discussed that at compile time and at load time, the address binding methods, what they generate identical logical and physical addresses. However, the execution time address binding scheme results in a differing logical and physical address spaces. So therefore now, because we just said that most of the operating system they are using a execution time binding scheme. So therefore they will all use different logical and physical addressing schemes. So in this case where we have different logical and physical addressing schemes, we usually refer to the logical address as also virtual address. In most of the books you will see that these two terms, logical and virtual address, are being used interchangeably, and the set of all logical addresses generated by a program is known as the logical address space, and the set of all physical addresses corresponding to these logical addresses is known as the physical address space, right. So therefore in execution time binding, right, the logical and physical addresses these two spaces will differ, because they are different logical address and different physical address which are used in the execution time address binding scheme. Now at runtime, mapping from virtual address is done by a hardware device called the memory management unit, or the MMU. Now this MMU has an important function. What is the function? That it will map the virtual address to the physical address. It will map the address which is generated by the CPU to the address which is used by the memory unit. So therefore it is known as the MMU, or the memory management unit. Now the base register that we had discussed is actually called a relocation register, and the value in the relocation register is added to every address generated by a user process at the time the address is sent to the memory, right. So what we are saying is that there is a base register. If you remember, the base register used to hold the lowest value in, which is available for a particular process. Now that value, that register is actually known as a relocation register, and it will have a value. That value will be added to all the addresses which are generated at the time of the execution, or at the time when the address is being sent to the memory, right. So for example, if we have a base register which has the value 14000, okay, then an attempt to the user to address location 0 actually dynamically means that the user is trying to access the location 14000. Why? Because this is the base value for that particular process. If the access is aimed to location 346, then actually it is aimed at 14346. The user program basically never sees the real physical address. Okay, the program can create a pointer to the location. Okay, it can store it in the memory, it can manipulate it, it can compare it with other addresses. All will be done with the address which is being created, or the address which has been calculated, which has been mapped to the location. But it's very important that the programs, they will never see the real physical address. They will only look at it as a logical address. The user program will only deal with logical addresses, and the memory mappings hardware, that is the MMU, will convert the logical address into physical address. So when the user program is looking at it, it is trying to access the particular location, it is trying to manipulate it, compare it, do anything with it, it is actually referring to the logical address, and there is a device, there is a hardware device which will convert this logical address into physical address. Then there is another important aspect when we are talking about how the utilization of the memory space is happening, that is known as dynamic loading, right. So we all understand that the computer system is based on the premise of maximum utilization of the available resources, whether that resource is the CPU or the resource is the memory. So in order to obtain better memory space utilization, we can use dynamic loading, right. So basically, what is dynamic loading? Dynamic loading means that a routine is not loaded into the memory until it is called. That is, all the routines, they will reside on a disk in a relocatable load format. The point when a particular a routine is required, only then it will be loaded into the memory from the disk. the main program is loaded into the memory and is executed. When a routine needs to call another routine, then the calling routine will first check if the other routine has been loaded or it is not yet loaded. So, if it is not loaded, then the relocatable linking loader is called to load the desired routine into the memory and to update the program's address table to reflect this change. See, if we are looking at this program, one routine is calling another routine. Now, if one particular routine is in the memory and the other is still not in the disk, then it needs to be called, and for this what is used? A relocatable linking loader is used. So, the whole thing is happening very dynamically, it is very demand based, right. So, control will be passed from the old routine to the newly loaded routine, because now the newly loaded routine will demand for more routines. So, what is the advantage of this kind of dynamic loading? That the memory is used very judiciously. A routine will be loaded only when it is actually needed, right. So, large amounts of code, when there is a scenario in which large amounts of code are needed to be handled infrequently, then such as for example, you have error routines. So, there are a large amount of these routines, but they are not coming in very frequently. So, in that case, dynamic loading will be very important, because it will come into the memory only when it is required, otherwise it will reside on the disk, right. So, in this case, when we understand that the routines are called very need based manner, then even though the total program size is large, the proportion that is used is actually very small. Why? Because only the routines which are required are being executed. So, dynamic loading, it does not require special support from the operating system, and it is actually the responsibility of the user to design their programs to take advantage of such a method. So, if you would recall that in most programming techniques that we do, we always talk about modular programming to create subroutines, so that this kind of dynamic loading can be done and the memory can be used very judiciously. So, operating system is not going to intervene in it, it will only help the programmer by providing some library routines to implement dynamic loading. Otherwise, this entire function of dynamic loading is taken care of by the programmers, right. Now, next very important topic or very important area that needs to be discussed when we are talking about how processes are allocated and deallocated in the memory, that is known as the swapping. Now, swapping basically means to interchange or to remove one thing and put something in its place, right. So, when we have a process in the memory and the process needs to be executed, right. Now, every process can be swapped temporarily out of memory to a backing store and then brought back into the memory for continued execution. We know this, that processes keep moving in and out of the memory, they go back to the disk, they go to the processor. So, they keep moving in the memory, in this whole system, right. So, swapping makes it possible for physical address space of all the processes to exceed the real physical memory of the system, right, because if you look at the entire address space, it may be smaller, right, but the number of processes which are executing, they may require much larger address space, but because of this swapping, every process understands that it has got the complete memory. So, the degree of multi-programming in a system greatly enhances, it greatly increases, because the swapping of the processes keeps on happening and processes keeps on moving in and out of the real physical memory of the system. Now, standard swapping basically is an old technique, but it is very important to understand this whole concept of how processes keep moving in and out. So, in standard swapping, what happens is that the process which moves between the main memory and a backing store. So, backing store is basically nothing but a fast disk, you can say, and it has got a very large storage space to accommodate copies of all memory images for all the users, because we are saying we are looking at a multi-user, multi-programming system. So, it provides direct access to all the memory images of all the users. Now, the system maintains a ready queue which consists of all processes whose memory images are on the backing store or in the memory, or they are ready to run, right. So, the backing store basically is a fast disk which will allow processes to be stored when they are swapped out of the memory. So, whenever the CPU scheduler decides to execute a process, it will call the dispatcher. So, basically dispatcher is the program, dispatcher is the function which will check, which process to be swapped in, which process to be swapped out. So, the dispatcher will check whether the next process in the queue is in the ready queue is in memory. If it is not there, there is no free memory region, the dispatcher swaps out a process currently in the memory and swaps in the desired process. It then reloads, registers and transfers the control to the selected process. So, dispatcher is doing this function of checking whether the process is there in the queue or not, and if there is space in the memory or not, and if there is no space, then which process has to move out of the memory so that the desired process gets the space to come in. Now, in this basically the maximum time which is going, the maximum time is going in context switching, right, because most of the time this change or this transfer is going to take. So, for example, if we have a system of, we have a user process, which is 100 MB in size, right, and the backing store or the disk has which is a standard hard disk, okay, with a transfer rate of say 50 MB per second. So, since it is a process of 100 MB, so 50 MB would mean that it would actually require 2 seconds for the actual transfer of the 100 MB process to and from the memory. So, it will take 2 seconds. 2 seconds means that swapping in and then swapping out also. So, in total it becomes 4 seconds. 4 seconds, and that if you look at in milliseconds, so it comes out to be 4000 milliseconds. So, therefore, we can understand that so much of time is actually, so much of precious CPU time is actually going in this swapping in and swapping out operation. Besides this also, besides the context switch cost which is involved, there are other factors also which constrain this technique or this scheme of swapping, right. For example, if we want to swap a process, so we have to be sure that the process is completely idle, right. Say for example, we have a process which is in pending IO, which is waiting for input output. Now, the process is waiting for an input output operation and we want to swap that process to free up the memory. So, however, if the input output is asynchronously accessing the user memory for input output buffers, then the process cannot be swapped, right. So, again another thing is that if the input output operation is queued because the input output device is busy, right. So, in that case also this scenario is not going to work, right. For example, if we have two processes, one is P1 and the other is P2, right, and if we have to swap out the process P1 and swap in the process P2, right. So, the IO operation might then attempt to use memory that now belongs to process P2 because the P1 was waiting for the IO. So, now what are the solutions to this problem? First is that a process which is waiting, which is pending for IO or executing IO operations, they should never be swapped into the operating system buffers. And secondly, that the transfer between the operating system buffers and the process memory, then only the process is swapped in. So, two conditions must be checked, that the process who is waiting for IO should not be swapped out, and any transfer between the OS buffer and the process memory will occur only when the process has been swapped in. If a process is being swapped out, then any kind of transfer will not help. So this is actually a double buffering that we are doing, which is again going to add a lot of overhead, right. So because now we need to copy the data again from the kernel memory to the user memory, and before the user process can access, this needs to be done. So therefore this is again a very large overhead on the system. So therefore, standard swapping is not used because of these costs, that is, the swapping cost or the context switch cost, or the other concerns related to waiting processes. It is not used too many times in the modern operating system because of these reasons probably. And now we have modified versions of swapping which are used in different systems like the Unix systems or the Linux and the Windows system. So we have more dynamic way in which the swapping function is going to work. So there are different variations of the swapping function which work. So swapping is normally disabled in these operating system, but it will start if the amount of free memory falls below a threshold amount. So then the operating system will see that after a certain point the memory is falling below a level, so then certain processes need to be moved out, and then the swapping is again halted when the amount of free memory will increase. Another variation of this swapping involves swapping portions of process rather than the entire process. So therefore we will have the decrease in the swap time. So instead of the entire 100 MB process moving out of the memory and coming in, only a certain portion can be swapped out so that the new process can be accommodated. So these are few strategies or few variations of swapping which can be used. Now when we talk about allocation of memory, we are talking about how processes are using the memory, right. So the main memory, it has to accommodate the operating system and it has to accommodate the user processes. So therefore memory is generally divided into two portions, as we've seen earlier also. One is for the resident operating system, which is always going to reside in the memory, and then there is another portion which is used for the user processes, right. So now operating system is generally, it can be placed in low memory or high memory either way, but because the interrupt vector is generally in the low memory, so generally operating system is also placed in the low memory, right. Otherwise it can be placed low or high anywhere. Now when we talk about contiguous memory allocation, now what happens in this? Contiguous means it is continuation, it is in continuation, right. So each process is contained in a single section of memory that is contiguous to the section containing the next process, that is, there is no break in between, right. So when we talk about memory protection in this, so when the CPU scheduler will select a process for execution, right. So the dispatcher will load the relocation and the limit registers, right, with the correct values as part of the context switch. Whenever the scheduler is asking another process to start, then all this information needs to be shared. That is, what is the value in the base register, what is the value in the limit register, okay, and what is the context switch information. Now every address which is generated by the CPU, it needs to be checked against the base and the limit register, because we know that protection has to be ensured. Both the operating system space is to be protected and the other user program space and data is to be protected from any running process. Then the relocation register, or the what we said as the base register at some time, relocation register scheme will provide an effective way to allow the operating system size to change dynamically. Only then the size can be changed. So this flexibility is very much desirable, because the operating system contains code also, it contains buffer space for say device drivers or for any other programs of the operating system. And if the device driver or if that particular service of the operating system is not commonly used, then it is not essential to keep that particular code and data in the memory, and instead we can use that space for other purposes. So such code is sometimes called the transient operating system code, because this code comes and goes as needed. When the particular device will be needed, the device driver code can be brought in, otherwise it can be kept out, right. So it keeps on changing the size of the operating system during program execution. This kind of transient operating system code can be used. So this shows how the relocation and limit registers are used for moving out and moving in of information, right. So when we talk about memory allocation, so one of the simplest methods for allocating memory is to divide the memory into several fixed size partition. This of course is an old technique which was done. So several fixed size partitions are created, and each partition will hold exactly, which contain exactly one process, right. So in this case the number of partitions will control the number of multiprogramming. If you have 10 partitions, then you can only run 10 programs in that system, right. And if a process is selected from the input queue, the process is loaded in the free section, and when the process will terminate, only then the partition will be available for another process. So therefore this entire memory allocation scheme was very rigid, and therefore it is no longer in use. Instead of this, now what we use is variable partition schemes, and in variable partition scheme the operating system will actually keep a table indicating which part of the memory are available and which are occupied. So the variable partition scheme is a better scheme, and it uses dynamic allocation of the memory spaces to the incumbent processing. So we will be discussing the variable partition scheme in the next lecture. Till then, please keep watching CEC. Thank you.